Imagine you're a doctor trying to pick the best treatment for a patient, based not on guesswork, but on data from thousands of similar patients. Or a business trying to decide who should get a special discount, or a government deciding who deserves a job training program. This isn't science fiction. It's personalized decision-making, and it's powered by something called offline policy learning. At its core, offline policy learning uses past data to teach a machine how to make smart, personalized choices, without ever having to run risky experiments. But here's the catch. The data is messy, incomplete, and biased. Say you want to test a rare treatment, but only a tiny fraction of past patients ever received it. That makes it hard to know how well it would actually work, because the data doesn't show it clearly. This is the high variance problem. When your estimates are too noisy, they can mislead you. And if your system gets misled by a lucky but wrong guess, say a treatment looks great because of random noise, it could end up choosing a worse policy. That's a real danger. So what if we could trim the noise, without throwing out all the useful information? Enter weight clipping. Instead of blindly trusting every data point, we clip the most extreme, unreliable estimates, like cutting off the tails of a bell curve. Think of it like a filter. We keep the stable, trustworthy data and ignore the wild outliers that would skew our results. But here's the problem. Most existing methods pick this clipping threshold through trial and error, using data to tune a knob. That makes it hard to use in the next step, learning the best policy. Because now you're not just optimizing a policy, you're also optimizing a threshold, which depends on the policy. It's like trying to find the best route while adjusting the map as you go. But what if we could mathematically find the perfect clipping threshold for any policy by minimizing the overall error? Not by guessing, not by tuning, by calculating it. That's exactly what researchers at the National University of Singapore and Tsinghua University did. They developed a new method called Optimized Clipped Doubly Robust Learning, or OCDRL. Their breakthrough, a closed-form solution, a precise mathematical formula that tells you the best clipping threshold for any policy before you even start optimizing. This turns a tangled, two-step problem into a single, solvable one. But even then, there's a hurdle. The math is discontinuous. That means small changes in the data can cause big jumps in the outcome, making it tough to compute. So they took inspiration from advanced math and rephrased the whole problem as a Heaviside composite optimization problem, a fancy name for a framework that handles these jumps cleanly and efficiently. And to solve it fast, they used a clever algorithm called progressive integer programming, which solves the problem in smart, iterative steps, focusing only on the most important parts at each stage. The result? A system that's fast, accurate, and scalable, even on massive datasets. In tests, OCDRL didn't just match the best methods, it beat them. Whether it was choosing the right medical treatment, setting prices, or targeting job training, it learned better policies, especially in situations where data was sparse or noisy. And in real-world data from a randomized trial on weather insurance, OCDRL boosted expected profits by over 1%. A small number, but huge when you're managing millions of customers. Why? Because it didn't just reduce noise, it balanced the trade-off between bias and variance. It wasn't too cautious. It wasn't too greedy. It was just right. So next time you get a personalized recommendation, whether it's a treatment, a deal, or a program, remember, behind the scenes, smart math is working to make sure you get the best choice, not just the loudest one. This is the future of data-driven decision-making, accurate, fair, and built on solid science. Thanks for watching. If you like this, hit like, subscribe, and let me know what kind of AI-powered decisions you'd like to see next.